Welcome to the lab portion of the Full Stack Deep Learning 2022 course. In this video, we're going to go over at a high level the text recognizer application that we'll be building through the rest of these labs. We'll also see how to get started with the labs on Google Colab, and we'll get comfortable with this Jupyter Notebook format that we'll be using for the labs. So we'll start off at the lab GitHub repository. You can find the link for this in the description of this video. This repository is where all of the material for the labs is saved. And if we just scroll down a little bit to the README section, we can find a description of the labs and all of these badges that say open in Colab. So these are what we're going to want to click to start working on the labs. So let's go ahead and click this button to try out this first lab that just does an overview of the application architecture for what we're going to be building this time. Now, here I am in a Jupyter Notebook environment that's being hosted by Google. Completely free. All you need is a Google account. So you might be asked to sign in or create a Google account if you don't have one. But once that's done, you've got a Jupyter Notebook that can run Python for you. So let's go ahead and start running code. If I click there on that cell and then hit either this play button here, or hit the Shift Enter, give it a second to connect, and our code is executed and pulled in our application and shown it inside of the notebook. The Jupyter Notebooks are composed of mixed different cells. So you can see that as I navigate up and down using the arrow keys, you can see there's a highlight coming up that's moving between the different cells of the notebook. Each cell is either a markdown cell that's got text and media in it that's describing what's going on in the code, or it's got just plain code in it. And then we can see the outputs underneath the cell. This cell brought in this iframe class and then used it to embed this application that we're going to build, the web page for it, embed it directly in this notebook. So notebooks are really great for mixing explanations and code and interactive components maybe built by that code. It's really ideal for these kinds of educational settings, or it makes for really awesome documentation. And some folks even do all their development in notebooks so that they can have this kind of rich interactive experience at their fingertips at all times. The first thing that we've done here is embed the application that we're going to build inside of the notebook as an iframe. But just to underscore that we're building a web application here for our text recognition, I'm just going to go ahead and open that link. This is the web page. We're going to build a web page that looks like this one. And what we see on the left is where we can put images for our text recognition system. Go ahead and grab one of these example images down here and submit it and see what happens. So if we wait a bit for our tensors to flow, we get out the output. So on the left, I read, we believe that a comprehensive medical service, free to the patient at the point of need and with one standard for all sick people, etc. Let's take a look at this output. So this is a Python string that came from our text recognition system. And it says, we believe that a comprehensive medical service, free to the patient at the point of need and with one standard, there's an E there. So it's not perfect. It's making some mistakes, but not bad. On this input, it does a pretty good job. There's some other samples there. And you can, if you like, upload your own inputs or edit the inputs that we have. So what would happen maybe if we zoomed in on that section where we had the mistake previously? We can submit that and take a look. Looks like the error goes away. There's some effective context here that's causing the network to make the mistake there. These interactive applications with models embedded in them are helpful even during model development. Hopping back to that Jupyter Notebook, let's continue through it and see how this app gets built. There's lots of text in this notebook that goes through all of the stuff that I'm going to be talking about at a high level in this video in much greater detail and talks about other choices for how we might have built this application. I'm just going to hit the highlights here and just strongly recommend that you check the notebook out for yourself and read through the text, check out some of the links. What we were just looking at above was the front end or the user-facing component of the application. We're going to build that entirely in Python in order to keep things as simple as possible, in order to make it possible for one person to be able to build this entire application and understand the whole thing themselves. But that front end's not the whole thing. The front end is just the thing that we render, that we show to people so that they can interact with our application. The model doesn't have to be in the same place. The thing that takes in images and spits out text, that machine learned algorithm, that model, doesn't have to be in the same place as the front end. For our application, we put our backend in Amazon Web Services Lambda, which is a tool for building serverless applications. We'll talk in detail about what that means and why you would choose that for your machine learning models. But the most important thing about this front end back end distinction is that our front end and our back end are independent of each other. So just because we've built this front end that looks like what we just saw that was built in Python, that doesn't mean we can only use our model in that context. So this cell here just runs a quick ping to that backend model, sends it an image, and then waits for it to get back with the predicted text. So we use some Python libraries here that are designed for working with web services. You can check out the comments on that code for details on how it works. We sent a URL to an image and we get back the text that was in that image. So I read, and since this is election year in West Germany, Dr. Adenauer is in a tough spot, Joyce Egginton cables. And that's what the Python string above reads. So our model was able to get the text there right. We have this raw string and we can interact with it with our Python code, so we can put it somewhere else. We can interact from the command line as well if we want, do our front end in JavaScript. We've got these two separate pieces. To see how these pieces fit together and how they relate to the rest of the application, let's pull up a little diagram here. This is an interactive diagram built with Miro, which is a nice visualization tool that lets us see how all of these pieces fit together, nicely embedded in this Jupyter notebook here. Don't even have to go to another web page. So we were starting up here at this user session. So that's the person interacting with our model. And they're talking to that front-end server that's in Python using the library Gradio. And that front-end server is doing a couple things. It's sending requests to that back-end that does our predictions in AWS Lambda. And then you may have noticed that those buttons for flagging that allows users to give feedback on how the model is doing. And we'll use a tool called Gantry to take in that feedback, analyze it, and use it to improve our models. The information for how to run our server and how to run our backend, those live in a container registry on Amazon Web Services. Containers are built using Docker. So this is the handoff point between the way that we build models and the way that they end up in production interacting with users. So I think it's helpful at this point to actually stop and zoom back out and start over at the beginning, to go from the training of models, which if you've taken a class that covered deep learning and talked about building models with PyTorch, training on GPUs, that'll be familiar to you. And then through the process of iteratively building a model until we're ready to put it in production. So we'll approach the handoff from the other direction. So to start off, we need to determine what kind of computers we're going to use to build our neural networks. And because neural networks operate by doing sequences of really large matrix multiplications and other array operations that are much faster on GPUs than on CPUs, we're going to need GPUs to do our computing. That's one reason why we're using Google Colab as one of the ways to deliver the labs. It's because Google Colab comes with free GPUs. To set that up in any Colab is to go to runtime, change runtime type, and pick a hardware accelerator and pick GPU. So that should already be the case for this lab for you. And to check that we actually have that GPU, we can run this command, NVIDIA SMI, that's kind of like a top command or a check of what processes are running, but just for the GPU. So we can see we've got a GPU. It happens to be a Tesla P100. You might get something different, and nothing's running on it yet because we haven't done anything. For building our full application, we use the Lambda Labs GPU cloud. You should check them out if you're interested in having access to more compute than just maybe your home machine or what Colab provides for free. Because we're doing all of our really heavy work on the GPU, we actually don't need to write the majority of our model development code in some fast language. In the end, we're going to be running stuff on a GPU with lower level libraries anyway, so it makes a lot of sense to use a language that's easier to write in, even if it's a little bit slower, because the performance bottleneck is the stuff that's happening in C++ on a GPU. The language that people use in deep learning is Python. There's really great libraries libraries for developing neural networks in Python. Libraries that do GPU acceleration from Python and also have the things that we need to train neural networks, like automatic differentiation so that we can run gradient descent easily. So the library PyTorch that kind of bridges the gap between Python and C++ gives us that GPU accelerated array math that we need, along with a bunch of neural network primitives and architectures. So this cell just demonstrates the basic way to interact with Torch, creating tensors or arrays, manipulating them mathematically, and then asking for gradients. Even PyTorch is a little bit too low level for when you're developing neural networks. It doesn't include a high-level framework for training neural networks or any of the other kinds of engineering type tasks you need, like saving your work as your model is training. So we use PyTorch Lightning as our high-level training engineering framework. They've got really great documentation for PyTorch Lightning, including a bunch of videos like this one embedded in the notebook. We'll talk a lot about how to use PyTorch and how to use PyTorch Lightning in a future lab. So we've got the libraries that we need to build our models. What we're missing is the kind of developer tools around model building. Creating a machine learning model is kind of like writing code. We're trying to create a computer program that can do something, take some inputs, return some outputs. It's just that this computer program happens to be a giant pile of numbers inside of tensors. And so because things are similar to general software development, we want developer tools, but because they're so different, we need slightly different developer tools. One of the most important things that we need is the ability to sort of track what's going on as we're making changes, and just baseline Git for version control doesn't do a great job for that. So the tool that we use to solve those problems, to track our experiments as we're trying out different configuration values and to track the artifacts or large binary files that we generate as we're doing those experiments, we choose weights and biases. So let's pull down a page from weights and biases and embed it in the notebook like we did with our application. So you can see there's lots of information here. There's charts that tell how our model was doing over time and across epochs, the inputs and outputs of our model, the ground truth labels, and then there's all kinds of other information, like system metrics included as well. Lots and lots of rich information that gets logged for us using the weights and biases tool. We can also take that information and turn it into nice dashboards for communicating results to people. Toss these on pull requests, use them as blog posts to share our work, for internal communication, use them for checking on long-running training jobs, all kinds of things. So we incorporate that information and add annotations and additional information to make it easier to draw insights. Once we've trained and developed our model, we've run our experiments, we need to turn that into something that we can use in production. PyTorch Lightning will be, throughout training, saving the current values of the weights of our model to disk. We store those on Weights and Biases Cloud, and then when they're ready to be deployed to production, compile them down to an artifact that's a little bit more independent, that doesn't require all of our development code. Because we've stored that artifact on Weights and Biases, we can take a look at it. And so our model file is saved alongside a bunch of really useful metadata and other information. So we can see the lineage of this artifact, what other artifacts were generated along the way to creating it, and which jobs were run in order to create those. We've now made it through the entirety of the application, from training a model all the way up to putting it in production and interacting with it as a user. So let's take a look at that diagram again. We've looked at all of these pieces in this short video, and over the course of the labs, we'll see how all of these pieces are put together to create a working, continually improved machine learning application. I'm looking forward to it.